Hello, everyone. Welcome to Math 1510 Deep Learning Theory and Data Science. Today, we're going to embark on a new journey. For those of you who have got lost in the sea of measurements of DeepNet spectra, today is the time for you to rejoin the the course because we're starting something slightly different. And as in previous topics, we're going to start with a small introduction to the topic. So in particular, the topic we're going to discuss is of infinite width deep nets. What is an infinite width deep net? Does anyone know? What do the words infinite width, deep net evoke in your mind? What do you see? The width is infinitely wide. That is correct, yes. So the width of the network is basically the number of channels in a convolutional layer. And in a fully connected layer, it's the number of rows, rows. So if you write in PyTorch, a fully connected layer with two parameters, then the first parameter or the second one would be considered the width. Now, before we can talk about those infinite width deep nets and why we care about them, we need a small introduction to kernels, which is the topic for today. So let us begin with a motivating examples. Assume that your goal is to classify the following data. So here we can see red pluses and blue circles. This is often referred to as the XOR problem. Does everyone know what XOR is? You do? Okay, so let me just briefly X XOR Y can be explained through the table X, Y, 0, 1, 0, 1. And then if you do XOR between 0 and 0, you get 0. 1, 1, you get 0. 0, 1, you get 1. 1, 0, you get 1, right? And so the plot that is being presented to you on this slide represents XOR problem. Why? Because you can think of this as being 1, of this cloud as being 1, as this cloud being 0, and this cloud being 0. Do you see how this is XOR problem? I mean, why is it called XOR problem? Essentially, the reason why it's XOR problem is because the true classifier here would be some type of XOR function, right? That would take into account the X and Y axis. Now, can anyone tell me why is this problem of interest? Does this problem strike you as particularly interesting? Or is this just yet another classification problem in your life? Not linearly separable, but still simple is the correct answer by Etienne and Amirez as well. So indeed, you cannot separate this data through a linear classifier no matter how you try. This does not separate, this does not separate, and so on. And so this is a challenge for a linear classifier that shows the limitation of linear classifiers. And so what one might do is use what? is use, a different, what happened? A different representation of the data. So imagine that we take our data, which had two coordinates. So let's denote this by, so this is x1 and this is x2, right? So two coordinates. Imagine that we take this data, which is a tuple of x1 and x2, and we just map it to a different tuple, right? So x1, x2, x1 times x2. Maybe at this point we should do a quick survey of how many people know about kernel methods in machine learning. Is it 100% of people? Is it 50% of people? Is it 20% of people? Is 0% of people? No, a bit. Okay, so Andrew, this lecture is dedicated to you personally. I feel like we should have started with this concept from the beginning, you know, dedicate each lecture to a single student. Maybe like put faces of that student throughout the lecture or something. Maybe next iteration. So basically what we're doing is we're taking x1. So here x is basically a tuple of x1 and x2. And we are mapping it to a new tuple of x1, x2, and x1 times x2, right, in R3. Why would you do that? Because if you use this representation of the data, you can call this a feature vector, then suddenly the data becomes linearly separable. So notice that we have here x1, here we have x2, and here we have x1 times x2, right? And now the data is linearly separable. What does it mean linearly separable in R3? It means that there exists a hyperplane, right, that separates the data. And indeed, you can see here the hyperplane. And so this is very intuitive because in the XOR problem, what you care about, if you look at this, this, basically you care about whether you're in the first quadrant or the third quadrant versus whether you're, so if you're in the first quadrant or the third quadrant, then you're in one class. If you're in the second or fourth, you're in another class. Do you remember quadrant from school? Yeah, okay. Okay, so this is the motivation for transforming data into feature vectors, which are ultimately going to be pretty high dimensional. And so this is the key idea in kernels. The idea is that if your data is not linearly separable, and in reality, you know, all data is probably not linearly separable, then what you want to do is transform the data into some higher dimensional space where it hopefully is linearly separable. Now, at this point, you might be worried that if we're transforming our data to some high dimensional feature vector, then doesn't that mean that our algorithm, you know, whatever we're doing, the classification is going to be very slow, very inefficient, right? Because if you work with high dimensional data, everything becomes more demanding in terms of runtime and memory. And it turns out that the runtime and memory efficiency is not actually a problem due to a trick. So in order to introduce the trick, let us look at a very simple algorithm, which is called ridge regression. So this is a very simple algorithm where you have a data set of xi and yi. Xi are inputs, yi are targets. You can think of these as labels, for example. And you can see how here we're doing a linear classifier W, which is dot producted with your input Xi. We're comparing the prediction to the target, and we're using the mean squared error loss. And we're also penalizing the L2 norm squared. So this penalty is what's called the ridge penalty. Ridge means L2 norm squared penalty on the parameters. Now, one can easily solve this optimization problem in closed form expression just by calculating a derivative. Just by calculating a derivative with respect to what? With respect to W, which is what we care about, right? And we actually did similar things, if not exact things, in previous lectures. So I will not go through the details. But what's important to see is that I'm just calculating the derivative with respect to W and equating it to 0. Then I'm massaging the expressions until I can obtain a closed form expression, right? So the closed form expression is W is equal to the sum of outer products of your data plus lambda times identity, where this lambda comes from here, right? And there's an extra, and then this is inverted, multiplied by sum over xi times yi. Okay. Now, here you can see the intuition for why ridge regression is useful from the perspective of numerical analysis. The reason why ridge regression is useful is that if you didn't have ridge regression, if you had no ridge regression, it would be equivalent to setting lambda to 0, right? And then you would just have the inverse of this matrix. But the inverse of this matrix sometimes is, maybe this matrix is not invertible, or maybe this matrix is not representative of your true population statistics. Imagine, for example, that your xi were distributed as a normal 0, 1, and imagine that your number of samples was very small, then this quantity might be very far away from the population second moment of an identity, right? So that's a different perspective on why ridge regularization is useful. It's kind of like a regularization of your covariance matrix or second moment matrix. But that's besides the point. What's important is for you to understand that this equation here can be written in a very compact form, which is XX transpose, where X is defined to be a matrix which contains in its columns x1 through xn, right? And y is a vector that contains the different labels. So it's just y1, y2, and so on, right? So if you remove this lambda identity, this is literally linear algebra, linear algebra, system of equations that we love and cherish, okay? Now, what we're going to do now is we're going to say the following. Imagine that this data is not linearly separable. Then the previous XOR example taught us that what we should do is replace the data with some feature vectors, right? And that's what we're going to do. So, So here, what we're going to do is take the objective from the previous slide and just change xi into phi of xi. Very simple, right? So we're just replacing the data with the feature vectors. Now, we can, at this point, just repeat the same steps that we did in the last slide and obtain, again, the optimal classifier. So in this case, the optimal classifier is going to be phi x transpose plus lambda I inverse times phi xy. So if X was a matrix of x1 all the way to xn, then phi of x is just a matrix where each column is phi of x. So it's phi of small x, 1 all the way to phi of small xn. Does this make sense? So it's just a matrix of the feature vectors. Okay. Now, notice that there is an issue, a potential issue with this classifier. Can anyone identify a potential issue with this classifier? A potential issue that could be so detrimental that this would be not practical.
I guess if the dimension of phi is large, then this matrix is really big, and then inverting that is tough.
Yeah, exactly. Thank you, Tristan. Indeed, the issue is that phi could be very high dimensional. Let us highlight the words high dimensional. Very. And in fact, in some cases, it's going to be so high dimensional that it's going to be infinite dimensional. Infinite dimensional feature vector. Insanity, right? Insane. And so what we would like to do is to avoid having to invert matrices of size infinity by infinity, right? That's a good thing to avoid in life. And so what we're going to do is we're going to use a trick. Linear algebra comes to our rescue. Linear algebra is saying the following. Notice that there is something called a push-through identity. A push-through identity is saying that if you're trying to calculate identity plus AB inverse A, then in reality that's equal to A times identity plus BA inverse. So this is actually very, very, very simple to prove. The proof is just as follows. You do, let's see if I get it right. Identity plus AB times A is equal to A times identity plus plus BA, right? So this is equivalent. And now if you multiply on the left and on the right by identity plus AB inverse, or identity plus BA inverse, you get this equation. Do you see it? So you just multiply by this thing on the left. If you multiply by this thing on the left, and I guess I should switch the order. Let me just switch the order, and then it will become super clear. So let's say we multiply by identity plus AB on the left, identity plus AB inverse on the left, then this would be canceled, right? And here you would get identity plus AB inverse. So this is this, and here it's canceled. Do you see that? You do. Okay. A very nice, very simple. Why is it called a push-through identity? Does anyone know? Does this evoke any push-throughs in your mind? Do you see what's being pushed? It's a beautiful name, I must say, push-through identity. You know, when you have an identity, the number one thing is give it a good name. A is being pushed through. That's exactly correct. You see, on the left-hand side, A is on the right, and then you're pushing it. It's like go inside, and then it appears on the left, right? Very cool. So in the future, whenever you want to push a matrix from one side to the other, you recall a push-through identity exists. Now, how is this useful to us? This is useful because if you look at this equation, which is equal to our classifier, then this equation, you can apply here the push through identity. So we're going to push through the phi x to the other side, right? And if you do that, this is what you get. Now, why is this a useful manipulation to do? Why is this useful?
I guess now the dimensions of the matrix you want to invert are much smaller.
That is correct. Thank you, Tristan. So now the dimensions of the matrix we're trying to invert are the dimensions of this matrix. So let us write explicitly what are the dimensions here. So let's denote it by number of features times the sample size n, right? So that's the dimension of phi of x. And so originally, we had to invert a matrix of size number of features times number of features. But now it is sample size by sample size. Now, is this a significant improvement? Maybe, maybe. So for example, if you have a MNIST data set, then you have 50,000 examples, and you would have to invert a 50,000 by 50,000 matrix, which you can in fact do these days. You can in fact invert such a big matrix. Okay, now notice also that this classifier is still suffers from the issues that Tristan mentioned beforehand, namely that classifier is still, notice it's still of dimension number of features. So let's just say features, right? Because phi of x has number of features rows. So we haven't solved our problem, we've just partially solved it. Okay. And so what we're going to do now is we're going to have a key observation. Is this problem you only consider number, what? Is this problem you only consider number of features too high, not the number of samples, right? Since there are high dimensional problem in which n is infinity. Yeah, we'll get to that, Amireza. That's a good point. Yeah. So what Amireza is saying is that sometimes the sample size is incredibly large. And so if you need to invert a matrix of size sample size by sample size, you have an issue. And that is in fact the number one issue with kernel methods, which is why people, maybe I shouldn't say they don't like it, not to get hate letters or something from kernel people, but this is the number one issue, I think, with kernels. Okay, you're touching on a good point, Amireza. So let us consider the following key observations. Imagine that we take our classifier W from the previous, this is W, from the previous slide, and imagine we applied to some test example, a new example, right? A new cat emerged, and you would like to classify it, whether it's ginger or whether it's brown. And so what do? You take this new cat, and what you have to do, okay, there is a typo here. Actually, this should be 5x0. My mistake. What you have to do is when classifying this sad cat, sad like this, not sad emotionally, what you have to do is you need to extract the features of the cat, right? So you want to take the cat and you want to extract the features of this new cat phi of x0, and then you want to apply the classifier on the features of the cat, right? Because you cannot apply a classifier which is trained on features just on the pixels of the cat, let's say. You need to transform the cat to the features and then apply the classifier on the features. And so if we do that, we get here phi x0 transpose or dot product with the classifier from the previous slide. And now comes the big observation, which is our classifier only depends on feature inner products. Let us highlight this. Remember these words. This is very important. Highlight 3 times, 4 times. So this is the main observation. The only thing that is important is the inner product between features. The feature vectors themselves are of no significance. So how can you see this? So first of all, notice that this matrix is of size sample size by sample size. So let us write it more explicitly. So this matrix here would be something like inner product of phi x1, phi x1. Then it would be inner product of phi x1, phi x2. Inner product phi x2, phi x1. Inner product phi x2, phi x2, right? So this matrix only depends on inner products of feature vectors. Moreover, let us change color. This vector, this is a vector now, is a vector that looks as follows. So we're going to have inner product of phi x0 with phi x1. And then inner product of phi x0 with phi x2. What a horrible handwriting I have. I do apologize. You see, this is why I create slides, so you don't have to suffer with this horrible, horrible handwriting that I have. You see, this is the vector phi x0 transpose phi x. Does this make sense? And so you can see everything depends on the inner products of the features. Now, what is the kernel? The kernel is a function that takes 2 instances in your data, xi and xj, and outputs an inner product of their corresponding feature vectors. So this is the definition of a kernel function, dot product of feature vectors. Now, the trick is that we will usually always, not usually, always choose the features phi that will lead to a kernel that can be calculated extremely efficiently, which is a bit counterintuitive. If you tell this to a person on the street, they would think that you would design the features, right? That's what a normal human being would usually think would be the case. But in reality, what you do is you choose the kernel function. You don't choose the features. When I say choose, what does that mean? It means you have now a set of cats and dogs, right? You don't choose what is the feature vectors for the cats and dogs. What you do choose is the kernel function that's going to take a cat and a dog and is going to calculate some inner product. And we'll see examples of such kernel function. Is this definition of kernel functions feature inner products the most general definition? I mean, does it work with any well-defined inner product? You'll see in a second example, the most general. This is the most general definition I'm aware of, yes. I think the examples should answer your questions more concretely. But before we get to the examples, there is this important observation to be made here. So there is a very important theorem in kernels, which is called the representer theorem. And this theorem says something quite simple. The theorem says that your classifier can be written as follows. So here we can see the classifier. This is the classifier from the previous slides, right? So this is the classifier, and this should be again phi x0. Sorry for the mistake. Oops. Okay. Now, this is the classifier from the previous slide, and this is the feature of the new example, right? So the important observation in this slide is that notice that this quantity here, if you disregard the phi x and just look at this quantity, y is a vector and this thing is a matrix. If you multiply a matrix by a vector, you get another vector, and I'm going to denote this vector by alpha. So alpha is a vector and its dimension is Rn, okay? And so using this notation, we can rewrite the previous equation as sum over I from 1 to n, alpha I, phi x0 transpose phi xi. So I'm basically just writing the inner product. Let me highlight this. So the inner product between this thing and the vector alpha is written as a sum. Is written as a sum. A simple manipulation, But what's important to notice here is that at the end of the day, the prediction is going to be, you're able to write the prediction as sum from I equal to 1 to n of alpha I kernel function xi and x0, right? And so why is this key observation called the representer theorem? What do the words representer theorem evoke in your mind? Who is the representer and what is being represented here? In simple words, Jack, simple words, so a person on the street could understand. A linear operator can be represented as an inner product, even simpler words. So what is being represented here?
I guess the classifier is being represented as like the kernel function evaluated at the samples.
Yeah, exactly. So what's being represented is the classifier, and the representations are these scalars alpha I. So in the simplest possible words, your classifier W is a linear combination of alpha I from 1 to n of this kernel function xi, and here you just put a box. Sometimes people like writing it like this, right? So essentially, your linear classifier is a linear combination of your phi xi also. You can think of it that way, right? So what's being represented is the linear classifier. The linear classifier, let me write it in even simpler terms, actually. You write it in a simpler way. In the simplest possible way I can explain, the classifier is the sum from 1 to n of alpha I phi of xi. This is the representer theorem. what is being represented? The classifier, right? How is it being represented? As a linear combination of the feature vectors. Does this make sense? And so this is just coming from, let me highlight. So here you have the phi, here you have the phi, and here you have this quantity is this. Does anyone have any questions? And so here you can see the important observation that the implication of this is that you don't actually have to save the classifier. All you have to do is save these coefficients alpha I and your training data, right? You don't actually need to save anything except that. Now, if you remember, Amireza's concern was that this whole thing doesn't work if your data set is large. Again, Amireza's concern is correct, because notice that your XIs, right, that's basically your training data. If you have a training data of ImageNet, you would have to, given a test point, you would have to compute an inner product with all the images in ImageNet. And that is very unfeasible, right? Very unfeasible. So one way you can think of the classifier is as a special case of a neural network. So imagine that we have the following neural network. Here we have the input data x0, and you can see like a bunch of nodes. So in this case, it's 1, 2, 3, 4, 5 dimensional. And in the middle, you can think of each node as being the inner product of the input data with a certain training example, right? So it's equivalent to saying that the first weight is just something like x1, x2, all the way to xn, right? So this is what the first layer is doing. And then what you have is all of these. So essentially it's equivalent to thinking of the weights as encoding the training data, right? And the width of the hidden layer is the number of training examples in the data set. Each node corresponds to a different training example. And these nodes are all being connected through weights to your final prediction, which is basically this node corresponds to phi x0 inner product with the classifier W. And it's just pulling all of these kx0 x1 multiplied by alpha 1 all the way to kx0 xn multiplied by alpha n. It's just a different way to represent this using a neural network. It's not really useful. It's just a way to think about it. Okay, so let us look at some examples of kernels. The first example is called the polynomial kernel. The polynomial kernel is defined as follows. So k of xi and xj is equal to xi inner product xj plus a constant scalar to the power of d. Okay, very simple, right? Can we calculate this efficiently? Yes. Why can we calculate this efficiently? Because you take two vectors, you calculate the dot product, that's easily. That gives you a scalar, add a scalar, compute the power, done, right? Very simple. But behind the scenes, what's happening is that if you calculate this kappa xi xj to be equal to that, you can actually prove that it's equivalent to calculating an inner product between phi of xi and phi of xj, where phi of x is this long vector, okay? In this long vector, what you have is different, I guess these are called, I forgot the name for a polynomial which has a single term. let's just use the word polynomial, which has a single term, monomial. Yeah, I was thinking monomial. Thank you. So here you can see different monomials. So essentially, what this feature vector is doing is taking your data x and it's calculating products of different things here. And that's how it's creating the feature vector. Notice that if one were to calculate explicitly the feature vector, that would take a long, long time, right? Calculating all possible monomials would be very computationally demanding. However, taking two examples, xi and xj, and calculating an inner product, adding a scalar, calculating a power is very efficient. Is there any phi representation for any given kernel? Yes, I believe that's a theorem that you learn in some course in math. I'm sure one of the math students knows what's the course. I think it's the course where you learn about, I can check the number if you want in the end. I think I know which course. So yes. Here is another example of a kernel. In this case, it's called the radial basis function kernel, in short, RBF. And the RBF kernel is defined as follows. So the kernel of xi and xj is equal to the inner product of phi xi and phi xj, which is equal to simply xi minus xj L2 norm squared divided by 2 sigma squared, where sigma is some parameter that you can choose. And then you apply an exponential on that. Very simple, right? A very simple function to calculate. What is the complexity? Linear in the input dimension. Just subtract two vectors, calculate L2 norm squared, exponentiate. Very simple. However, one can show, and one does not show, but one could show that this kernel corresponds to a phi which is infinite dimensional. And so the phi is 1 x over 1 factorial x over, I think there's a square missing, x squared over 2 factorial x to the power of 3 factorial, and so on. Amiraz, I'm pretty sure the answer to your question is yes. I can give you the theorem at the end if you want. Okay. So in this specific example, you can see that one wouldn't be able to operate in the feature vector domain, right? Because you cannot operate on vectors of size infinity on a computer. Mathematically, you can, but we would like to use computers, right? And more generally, this is a proper definition of a kernel. So a proper definition of a kernel is that it's a function that goes from the cross product of a space of samples and a space of samples to R. And there's a Hilbert space here which defines the inner product that we keep talking about, and a feature map phi that goes from X to that Hilbert space. And basically the inner product can be thought of as a inner product over a Hilbert space. So that's usually how you formalize it. Yes, I believe so. Actually, feature xi, xj. Yeah, I think there is possibly a mistake. I'll fix all the mistakes and upload a new version to the website. So to summarize, here's the main point of this lecture. The main point is if your data is not linearly separable, then what you should do is transform it to a higher dimensional feature space where it would be linearly separable. And the kernel trick says that you do not operate in this high dimensional space explicitly, but rather you just calculate inner products between pairs of features, and those inner products are extremely efficient to compute. Now, in this lecture, I've shown you how to, it's called kernelize. Oops. Kernelize is a verb, kernelize. So there is an industry of people who kernelize algorithms. You can become part of this industry. By kernelizing an algorithm, what you do is you take your favorite algorithm, so it could be rich regression, but someone already did that. Could be a linear discriminant analysis algorithm, but someone already did that. It's called kernel linear discriminant analysis. Could be PCA, but someone already did that. So you see 3 dots. You just pick an algorithm, you know, your favorite algorithm that no one thought to kernelize before you. Rewrite the algorithm in terms of its inner products. So like rewrite it in terms of xi, xj, and then just replace the inner product with phi xi, phi xj. And then there you have it, your first kernelized algorithm. Does this make sense? So the natural question is, how is any of this related to deep learning? And that will be answered probably in the next lecture, So it seems like we're out of time, but I do have one more slide. I do not have more slides. So we're out of time and I'll stay for questions. Thank you for joining. And that's it. What are the benefits of kernelizing the algorithm? Is it from computational efficiency? The benefits are that by kernelizing the algorithm, you can separate data which is not linearly separable, as we saw. So for example, by using a ridge regression, you would not be able to solve the XOR problem, right? But if you use kernel ridge regression, then you can linearly separate your data. Is it sometimes impossible to linearly separate data by mapping to a finite dimensional feature space? Otherwise, what is the reason for considering finite dimensional feature space? So if there is one thing that deep learning has taught us, is that it is possible to linearly separate data by training a deep network, right? So if you think about it, do you remember the neural collapse lecture? The neural collapse lecture has taught us the following observation. If you have a bunch of data X that goes, or a single image X that goes into a deep network, right? And then you get as output H, and you plot these features in high dimensional space, you see that it looks something like this, right? I don't know which symbol is there. Maybe try. So what this implies is that the network, the deep network, manages to map data X to feature vectors H, which are linearly separable. So when Jack asks, is it sometimes impossible to linearly separate data by mapping to a finite dimensional feature space? It seems from deep learning that it's possible on very important examples that people care about. What is the reason for considering infinite dimensional feature spaces? What is the reason for considering infinite dimensional feature spaces? I think it's not quite, as far as I'm aware, I cannot think from the top of my head of an example where an infinite dimensional feature space would be able to solve, but a deep network would not be able to solve, if that makes sense. I mean, a practical example where you would need infinite dimensional feature space, cannot think of one. That's kind of why deep learning is popular, works well. I don't think it's a satisfactory answer to your question, though. I think the answer to your question is that empirically what we observe is that deep networks do manage to transform the data to a feature vector that is linearly separable.
So a question about the presentations. Are we not starting them on Monday then?
There might be a certain students asked me to perhaps delay them to the period of exams. And I was thinking of creating a poll where I would ask, would you like to have the presentations during the exams or not? I personally don't see why would you want a presentation during exam week. Yeah, and I also do want everyone to participate and see each other's presentations. What do you prefer, Luke? Do you have a preference that you're willing to share on record while this is going straight to YouTube? I can actually stop the recording.